We are going to start our derivative applications unit with two theorems. The first one is called the mean value theorem, and the second one closely related to it is called Rolle's theorem. The mean value theorem first is abbreviated MVT, and that's a pretty standard abbreviation. The first requirement, if you're going to use the MVT, is you must have a continuous function, and it also must be differentiable. So those two things have to happen first before we can even apply this. We're going to go through various interpretations of this theorem. The first one you see here says f prime of c equals f of b minus f of a over b minus a. You should recognize parts of this. This f prime of c, that was a derivative, and we know that that is also called an instantaneous rate of change, which we also refer to as slope of the tangent line. And on the other side, this f of b minus f of a over b minus a, we know that to be an average rate of change, and we refer to that as slope of the secant line. And what the MVT guarantees is a value c where the derivative, that is this instantaneous rate of change, equals the average rate of change. In other words, where the slope of the tangent line equals the slope of the secant line. Let's go ahead and look at it on this graph over here. I'm going to start first by drawing this secant line that's being talked about. And all the secant line is a line drawn through the endpoints A and B. So this blue line here is my secant line. And I can find its slope by just doing f of b minus f of a over b minus a. That is just the regular slope formula, y2 minus y1 over x2 minus x1. And that would give me the slope of this line. What the MVT is saying is there is a place on the interval from a to b. So somewhere on the interval from a to b, there's a spot on this curve where I can draw a tangent line that has exactly the same slope as the secant line. If you start on the left side of this curve and you just start imagining what the tangent lines would look like at various points, you can see, I'm drawing them in yellow here, that as I approach this maximum point right here, there's a place just before I get to the maximum that if I draw that tangent line, it is going to be parallel to that secant line and therefore have the same slope. And it's a little bit before I hit that maximum point, because once I hit that maximum point, I would be going horizontally and I'd have a slope of 0. So I've identified a point about right here where this tangent line is parallel to the secant line and therefore has the same slope. If I go down, that is this value c that's guaranteed by the mean value theorem. If I were to continue moving to the right, drawing tangent lines, I would hit this maximum and I would be going horizontally. And once I roll past the maximum, I would have negative slopes, which obviously would not have the same slope as that secant line. But I would keep going, and then I would hit a minimum here, and I would have a 0 slope right here. And as soon as I moved past that minimum, I would hit another place where I would have a tangent line that was parallel to my secant line. And that looks to be about right here, if I draw the tangent line. So I've actually found a second value of c. I'm going to put subscripts, call this one c1 and c2. The mean value theorem actually only guarantees one of these values. This particular curve actually had two of them. So just to summarize this MVT, if you have a continuous and a differentiable function and you draw a secant line through the endpoints A and B, this theorem guarantees there will be a place on that interval from A to B where you can draw a tangent line that has exactly the same slope as that secant line does. Let's take a look at an example using the MVT. And the first thing we have to do with any MVT problem is state that we have met the requirements, that is, that our function is continuous and differentiable. And I just make a statement saying that f of x is continuous on the closed interval from 0 to 2 and differentiable on the open interval from 0 to 2. And how do I know that? Well, this is a polynomial function, which is continuous and differentiable, so you just make that statement. And I'm going to pull down that formula that I have above. My interval is from 0 to 2, so that's my a and my b. Before I continue on, let me pull in a picture so you get an understanding of exactly what we're doing here. Here's a graph of f of x. This is that quadratic that we have. my interval is going from 0 to 2, so these are my endpoints, and that's where I drew this secant line, which is the blue dotted line here. And when I do this f of 2 minus f of 0 over 2 minus 0, I'm simply finding the slope of this blue line. And my job is to find a place in between 0 and 2, so on this interval somewhere from 0 to 2, where I can draw a tangent line that is parallel, i.e. has the same slope. So if I just kind of play around with this a little bit, I can see that right here at the very minimum, my slope is going horizontally and it doesn't have the same slope. But as I move to the right and I go into positive slopes, I can see about when I hit about right here, if I draw a tangent line approximately at this 1, when x is 1, I'm going to have a tangent line that parallels that secant line. So just graphically, when I look at this, I'm going to guess a value of 1. Let me go over here on the right side and go through the calculations and see what this tells me. So this f prime of c just means to do the derivative of f, and where you see the x, we're going to plug in a c. So our derivative up here would simply be 6c minus 2. And then f of 2 means we're going to take that 2 and I'm going to plug it in here and I'm going to calculate, and then I'm going to do the same with the 0. So I take the 0 and plug it into f of x. And f of 2 is 9, and you can see that from this graph as well, that when I plugged in a 2, I got a y value of 9. And f of 0 is 1, and that's this 9 minus 1 I have right here. And now all that's left is just to solve this equation. So 9 minus 1 divided by 2 is 4. If I add the 2 to both sides, I get 6c equals 6. And then divide by 6, and I get c equals 1. And that is the same one that I had approximated over here graphically. And here's another example for us to try. I'm going to start the same way by making sure that I'm allowed to use the MVT by stating that g is both continuous and differentiable. And when you have a rational function like this function is not continuous at x equals negative 4. However, if you look at our interval doesn't include negative 4, so we're actually okay as far as continuity and differentiability. And the next thing I'm going to do is find the instantaneous rate of change of g and plug a c in, and that just means the derivative, and set that equal to the average rate of change on this interval from 2 to 8. So my instantaneous rate of change has to equal my average rate of change. The instantaneous rate of change is just the derivative, so I have to do a quotient rule in finding this derivative. And over here it's my quotient rule, so it's the bottom times derivative of the top, which is just 1, minus the top, which is the x, but I'm plugging in a c, times derivative of x plus 4, which is just the 1, all over that bottom function squared. And on the right side, I have g of 8. When you plug in 8 in here and simplify, you get 2/3. So it's 2/3 minus g of 2 is a 1/3 divided by 6. And so now I'm just going to simplify from here. And what I see happen is that this c minus c just zeroes out, and I'm just left with the 4 in that numerator. And I just went off to the side to simplify this complex fraction over here. So this ends up being a 1 over 18. And to solve from here, I'm just going to cross multiply. And that brings me to c plus 4 quantity squared equals 72. And then to get rid of the squaring, I do a plus or minus square root of both sides, and I bring that 4 over. So I end up with this negative 4 plus or minus the square root of 72. So I'm going to break these up into the decimal equivalents. This actually gives me two answers. It's negative 4 plus the square root of 72 and negative 4 minus the square root of 72. And this gives me these two answers, this 4.485 and negative 12.485. However, I have to take a look at my interval from 2 to 8, and I see that my second answer actually is not on this interval, so that is not an answer I would present, and I would go with this one answer right here. So when you're doing these and you're giving your final answer, make sure whatever answer you give is on the interval that's given in the very beginning of the problem. I chose the next example so you could see how it might be asked on an AP exam. There's also a little bit of review embedded in this problem as well. So this is from the 2018, it's question number 4, and it's parts A and B that we're going to go through. So first it says that the height of a tree is given by a twice differentiable function h. H of t is measured in meters and t is measured in years, and we have select values of h of t in this table. Part A is actually a review question. It's asking us to estimate h prime of 6. So just a reminder on how we did that. We are asked to estimate the derivative, and all I'm given to work with is a table of h values. So what we did is we positioned this value of 6 on the appropriate interval, and 6 is between the 5 and the 7. So what we're going to do is an average rate of change using this portion of the table. And just remember, we're required to show the numbers from the table, so this is a mandatory step, and I get 5/2 as my answer. There's a second part to question A that says, using correct units, interpret the meaning of this h prime of 6. And what I know is that that is an instantaneous rate of change, so I would just say that as my explanation. My units of that 5/2, if you just look at the units of the 11 and the 6, well, the units on that were meters, so this is meters. And the 7 minus 5, the units on those numbers were years, so it's just meters per year would be that appropriate unit that I would use. So my interpretation would say the height of the tree is changing at a rate of 5/2 meters per year at time t equals 6. It's important that you acknowledge 3 things in a statement like this. Number 1, that it's a rate. Number 2, it asked for the units, so I need to say those units. And number 3, that it is a rate of change at that moment in time, at that time t equals 6 years. So you have to say what the 6 means in the context of the problem. Our MVT is going to show up in part B, so I first need to make sure that I have a differentiable and continuous function. All it tells me is that it is differentiable, but I know a differentiable function is also continuous, so I can make that statement. So let me see what this question is asking me to do. It wants me to explain why there's at least one time t on the interval from 2 to 10 where the instantaneous rate of change is 2. So what the MVT says is, if I can find a place where the average rate of change is 2, then by the MVT there's a place where that instantaneous rate of change is 2. So I'm going to go through this table and see if I can find an interval where when I do an average rate of change, I get 2 as my answer. And it takes a little bit of figuring and looking to find out. But if I look right here on this interval from 3 to 5, if I do 6 minus 2 is 4, divided by 5 minus 3 is 2, the 4 divided by 2 is going to be 2. So I kind of look around this table and I find a place where that 2 happens with that average rate of change, and I've identified it so I can continue on with this problem. And then I go ahead and show my average rate of change on that identified interval, which was from 3 to 5. And now I can use the MVT to say, since I found a place where the average rate of change was 2, that guarantees there will be a place where that instantaneous rate of change is 2 as well. And I just say that in a statement. So by the MVT, there is a value t on the interval from 3 to 5, because that's what I had identified up here on the interval from 3 to 5, where h prime of t equals the 2. And our last part here is on our other theorem called Rolle's theorem. And this one is not nearly as popular as the MVT, but what it says is that you, again, have to have a continuous and differentiable function for this to apply. And it has an extra requirement. It says that f of a has to equal f of b. In other words, our 2 y values have to be the same. So f of a and f of b have to have the same y value. So when you do that secant line, what happens is it's going horizontally. And it's just saying, therefore, your f prime of c must be equal to 0 as well. It must be going horizontally. And you know that that occurs at max and min points. So again, this one is going to have one value here and another value here. So my 2 values of c for this particular one would be right here, c1, and I would call that c2, because that's where I have that horizontal tangent line. The slope of the tangent line is 0, and that all happened because my f of a and my f of b were in line with one another and created this secant line that also had a slope of 0. And one last example in the spirit of the AP exam. So I have function f, continuous and differentiable. on my interval from 2 to 10, so from 2 to 10. And these are selected values of f. That's important to realize that these are only selected values of my function f. And I have to identify which statement is true. And I'm just going to take these one at a time and explain the false ones and also the true one. So part A, option A, says f of x is greater than 0 for the interval 2 to 10. And you might mistakenly think that is true because as you look at all of these values, I have a 20, and a 15, and a 10, and a 15, and a 20. You might think, well, those are all greater than 0, so let me say true on that one. However, these are selected values, so we have no way of knowing what's happening in between. So, for instance, at x equals 3, this thing might take a dive, and it might actually jump down here to a negative 10, and then back up to the 15, and we have no way of knowing it because these are just selected values. So I'm not going to pick A. And option B says f prime of 6 equals 0. If you think of this thing graphically, at 2 I'm at a value of 20, and at 4 I go to 15, and at 6 I go to 10, and at 8 I'm back up to the 15, and at the 10 I'm at a 20. If you think of it graphically, you might mistakenly think that since these points line up like this, that I hit a minimum value, and that's pretty much what this is saying, that I have a derivative of 0, which indicates a minimum value here. But again, for the same reason I couldn't choose A, I have no way of knowing what's happening in between these values. So even though it does look like a minimum value is happening at 10, at x equals 5, this thing might dip down below and go lower than 10 and not necessarily indicate that a minimum is occurring at x equals 6. So let's not pick B. And C is kind of that same train of thought, that even though it looks like, when I look at this graphically, it looks like this is increasing as I run past 8. It's not necessarily true because I could decrease, and without knowing what's happening on the in-between values, that could happen. So don't pick C, which means our answer has to be D. But let's take a look at it. So this is saying for some value x on the interval f prime of x equals 0. So if I look at that interval, I see that f of 10 is 20 and f of 2 is 20. In other words, my f of b equals my f of a. And that's exactly what Rolle's theorem says. If I have f of b equaling f of a, that I'm guaranteed to have a place where the slope of the tangent line is 0. So because my f of 10 is 20 and my f of 2 is also 20, if I were to do an average rate of change of those, I would get 0 as my answer. Therefore, I'm guaranteed to have a place where f prime of x equals 0. And that's about it for these two theorems. MVT shows up way more frequently than Rolle's theorem does. Just make sure prior to using either one that you state that you have a continuous and differentiable function. And also just follow the script and follow these examples, and you will nail it every time.